Hear me? Yeah. Okay. Hello. So today I'm going to talk about refinement reflection, a technique that we developed and implemented in Liquid Haskell that allows you to have complete verification using SMTs. So before I talk about what is completeness in verification, I'm going to start with what I mean by verification with SMT. And here I have my Fibonacci, my running example that you're going to see for the next 20 minutes. And it's a standard definition of Fibonacci. It says that it takes as input an integer I, and if I is less than or equal to 1, it returns 1, otherwise it recursively calls itself. So apart from the definition, I'm giving a refinement type as a specification for the Fibonacci function. So I say that the input of Fibonacci is an I, that is an integer, and this I is always greater than or equal to 0. And the result says that Fibonacci returns a value v, that is an integer, and it is always greater than 0 and greater than or equal to the input. So the goal of verification with SMT is to treat SMT as a black box so that I verify that the definition of Fibonacci actually satisfies the refinement type specification. So I start from my base case. I collect all the information from the program. Here that the result value v is exactly equal to 1. And from this information, I want to imply the result refinement. I want to imply that the value is greater than 0, and it's also greater than or equal to the input. So I have this implication from the information from the program to the result refinement, and I ask the SMT solver, is this valid? The SMT solver says, yes, it is valid. So I'm done with my first case, and then I go to the recursive call. Again, I collect a more complicated assumption about the program this time, and from this, I want to infer that the result refinement holds. So again, I have an implication, I give it to the SMT solver. The solver says that this implication is valid, so I can conclude that Fibonacci is actually verified. So this is how I do verification with SMT. And what is very important is that for this verification to be practical, all the queries that I am asking to the SMT should be decidable. And this is very important because if I go outside of this decidable logic, then the SMT may divert, so the user doesn't know what to do if it is in cases that the SMT is diverging. So we stay inside the decidable fragment. We have fast verification using SMTs. And the question here is, can we also have complete verification? So in this talk, I'm going to say that, yes, you can have complete verification. And I'm using two interesting techniques. One is called refinement reflection that intuitively says, take the implementation of the function and put it into the refinement of the result. And then with this, I can prove very interesting facts about my program. I can have complete specification. But then the proofs are very, very complicated. So we developed this technique that is called proof by logical evaluation to simplify away all the proofs. And all this is implemented and used in Liquid Haskell. So back to my fib example. I want to have this complete verification with SMT. And as an instance of this complete verification, I want to verify theorems about my Fibonacci function. So for example, I want to verify that Fibonacci is increasing. And this is expressed as for every natural number I want to prove that fib of I is less than or equal to fib of I plus 1. So I want to prove that using SMT. So the first question is, how do I represent this fib inside the SMT? And the answer is quite standard. So I'm going to use an uninterpreted function to represent fib in the SMT logic. So I represent fib as an uninterpreted function within the decidable fragment. But the only thing I know about fib is that it satisfies congruence. Same inputs, same outputs. So I don't know anything else about the implementation of fib. And the next question is, OK, so how do I connect the uninterpreted function fib with the Haskell function fib for which I have the implementation? So the standard approach is to use an SMT axiom to connect these two things. For example, an SMT axiom that connects the uninterpreted function fib with the Haskell function fib would say that for all inputs I, then the uninterpreted function exactly syntactically satisfies the definition of the Haskell function fib. But the problem with this approach is that the SMT then needs to instantiate this axiom, and then fib is a recursive function, so instantiation can go infinitely. So this approach is undecidable. If we use axioms, we can go in the undecidable fragment of the SMT logic. So as an alternative, we propose this refinement reflection that says keep the definition of the fib in the logic, but not for all i's, just for the i's for which you apply the Fibonacci function. So I'm just taking the syntactic definition of fib, and I am pushing it into the result of the refinement of the fib function. So I have the definition of fib just for the input I. And this is what all reflection is about, refinement reflection. So if you want to represent a Haskell function or a target language, a target function into the logic, you just take the definition of the function and you put it into the result of the refinement specification for the concrete i's for which you apply the function. Okay, so we represent functions as an interpreted function, functions in the SMT, and then with refinement reflection, we connect these uninterpreted functions with their target language definition. And a side effect or a third step is that when we're actually applying in the source language, in the Haskell language, the functions, then we're basically unfolding exactly once the functions into the logic. So here I say that if I apply fib to 0, then in the logic I am unfolding fib at exactly 0. This means that application basically turns into type level computation of one step. So if I apply in Haskell fib to 0, I know that fib is exactly equal, a fib of 0 is exactly equal to 1. If I apply fib to 1, I know that fib of 1 is exactly equal to 1. If I apply fib to 2, I know that fib of 2 is fib of 1 plus fib of 0, and no more. I don't go unfolding automatically, no more. And then I can go on and apply, for example, fib to arbitrary arguments to the variable I here. And if I apply fib to I know the definition of fib, but it is guarded by this I is less than or equal to 1, so I don't know what to do with that. But then from the context, I could have the information that, you know what, I is greater than 1, so then I can go on and unfold in the else branch of the Fibonacci definition. So I can apply fib to I, or to the I plus 1. And what is interesting is that these unfoldings is exactly the information that we need to prove our initial theorem that fib is increasing. So only this information, only these unfoldings in the previous slide is enough to prove that fib is increasing when guarded with the proper guards. But the guard here is Haskell function. So here the proof that fib is increasing is a Haskell function with the proper guards, the proper applications, and then all these blue functions are what we call proof combinators that are Haskell functions that exist there only so that the proof actually looks like a proof. So I express a proof of a theorem that fib is increasing as a Haskell function. I express the theorem as a refinement type that takes as input a natural number I and returns a value of unit type whose type has the property that I want to prove. And in the rest, I can just simplify the value of type unit away and have a simpler theorem. So in short, I can use this refinement reflection to do theorem proving, where theorems are expressed as refinement types, proofs are expressed as functions, and then I have a refinement type checker that basically checks that the function satisfies the theorems. And what is cool is that proofs are just functions. So the proof fib up is a function. So since it's a function, I can just go on and apply it and call it. So if I call fib up on 4, I know that fib 4 is less than or equal to fib of I, and then I can call fib up in variables, for example, I or j minus 1. And then I have theorems that I can use as lemata to prove more interesting properties. For example, here, I am using the fib up to prove that fib is also monotonic. So I have my theorem that says that for every natural number I and every j greater than I, fib of I is less than or equal to fib of j. And the proof is by induction or by Haskell's case splitting, where in my base case I call fib up on I, and the inductive case I call fib up on j minus 1, and also I am doing a recursive call. And all these are implemented in, so proofs are functions, we can call them. And also, what else we can do with functions? We can go on and abstract them. So this theorem says that a fib is monotonic, and it is using the proof that fib is increasing, and it is using the fib function. But what we can go on and do is go and abstract away the fib and the fib up. So have a theorem that says that for each function on natural numbers, if you give me a proof that it is increasing, then I can give you back a proof that is monotonic. And again, the proof is similar as before. So all these are implemented in Liquid Haskell. So I'm going to open up my favorite theorem prover now, that is the browser. So this browser basically is a Haskell module. I call it Reflection. And I am importing here proof combinators, the library that comes with Liquid Haskell and has defined all these blue functions. And I can run, which means that I am asking Liquid Haskell to check that the code is satisfied. Here I have the function that I showed you that says that for every function f on natural numbers, if you give me a proof that it is increasing, then I give you back a proof that is monotonic. And then this is an interesting metric. We call it termination metric that basically checks that f mono is terminating because y is decreasing. But if you see that as a proof, it basically says that the proof proceeds by induction on y. So if I come here and do a wrong recursive call with a y that is not decreasing, then Liquid Haskell will hopefully complain. And also, if I don't cover all the branches, then again, Liquid Haskell will complain. So Liquid Haskell makes sure that the proofs are mathematical proofs by proving that they are total, everything is covered, and also by proving that they are terminating. And okay, so here I'm defining fib exactly as in the slides. I am reflecting fib into the logic. Not everything is reflected by default. And then, as in the slides, I can come and prove that fib is increasing and use it to prove that fib is indeed monotonic. I am calling the higher order of mono to prove that fib is indeed increasing. So then you can use it to prove more interesting properties. For example, here is a very sneak preview of the section 3 of the paper that says that you can encode using refinement types in Liquid Haskell natural inductive proofs. So here I prove that for all properties P and Q, if for all x, P of x and Q of x holds, I am encoding for all as a function and conjunction as a pair. Then for all x, P of x holds, and for all x, Q of x holds. And the proof of this is just a Haskell function. And then we can go and do more Haskell-like proofs. So for example, we can prove list laws. And to do that, I am defining list append on Haskell lists. I am reflecting it into logic. And then I can come and prove properties about list append. For example, here I am proving that it is associative. I am proving that for every list x's, y's, and z's, x's append to y's and z's is equal to x's and y's append to z's. And the proof is proceeds by structural induction. I am case splitting. If x's is the empty list, then I am just unfolding the definition of append. And if x's is a cons, then I am unfolding. I reach a point that I need to call my inductive hypothesis. I am calling associativity on x's, and then I keep unfolding until I reach the right-hand side. So this is a proof. It is accepted by Liquid Haskell. To check its validity, what I usually do is I try to prove something wrong, and Liquid Haskell should complain. It is a proof, but it is verbose. It has too much information. So what you can do to simplify this proof is to use this magic flag that is called PLE ASOC that basically says, do all the unfolding by yourself. So instead of doing all the unfolding, you just pass unit. And in the inductive case, you just need to pass the inductive call. So all the unfoldings are automated using this PLE, and this is a much shorter version of the same proof. So in the rest of my talk, I'm just going to describe what is this PLE that automates the associativity proof. So PLE stands for proof by logical evaluation. And the idea is very simple. It says just go and unfold if you can unfold. So for example, if I have the theorem that fib is increasing, I have in my logic fib applied to I and to I minus and to I plus 1. So PLE is going to see these two terms that it could be unfold, so it is going to try to unfold them. Now, I don't know anything about I, so I cannot unfold fib of I and fib of I plus 1. But if I know from the context that I is exactly equal to 0, that I can go and unfold both these terms to 1. And if I know from the context that I is equal to 1, then again, I can go and unfold these two terms to what they evaluate to. So I can go and unfold fib of I to 1 and fib of I plus 1, which is fib 2, to fib of I plus fib of 0. And then, because PLE sees these two new terms, it is going to unfold them too. And at the last case, if I know that I is greater than 0, then again, I have fib of I and fib of I plus 1. And I know that they both unfold on the else branch of the fib, so PLE will go and unfold them. Then I have two new terms, and PLE would want to unfold them too. But I don't know anything about these values, so I cannot unfold, and I stop my unfolding. So this unfolding turns out to be very useful, because if we go back to the proof that fib is increasing, basically this proof proceeds by k-splitting and unfolding. The k-split is needed, but all the unfolding can happen automatically by the PLE. So this is a new proof that fib is increasing. So the idea of PLE is very simple. Go and unfold the functions if you can unfold them based on the context. In the paper, we prove that it is terminating. And this holds because all the reflected functions that PLE unfolds are actually provably terminating. We prove that it is complete, which means that if there are any unfoldings that could be done, PLE will go and do them. And also from our evaluation, we saw that PLE greatly simplifies the proof generation. So in the evaluation, we used reflection and PLE on many interesting benchmarks that I'll show you in a while. But here I am pointing out the interesting ratio that we care in the evaluation. And this ratio is the ratio of the proofs to the implementation, where by implementation I mean the functions, the Haskell functions that you can actually run, like PLE or append. And by proofs I mean the specifications, the refinement type specifications that express the theorems, and the proof terms, the Haskell proof terms that evaluate the theorems. So we see here that PLE drops this ratio from 2.4 to 1.6, while the running time of the verification remains about the same. So we used, in our evaluation, a bunch of benchmarks. We evaluated reflection and PLE on arithmetic properties, like Fibonacci, on class laws, the easiest of which is the associativity that I presented, on higher order properties, like universality of fold, on functional correctness like chance-solver and unification, and we have a test case on proving deterministic parallelism. So the ratio drops, the ratio of proof to specification drops at its benchmark, but it drops differently. For example, in the class laws that are proof-heavy, the ratio drops from 4 to 2, while in the deterministic parallelism that's application-heavy, the ratio drops from 1.7 to 1.3. So in the paper, you can see a lot of details that I'm not talking about, like the proof that PLE is complete and terminating. There is a comparison with other theorem provers, and also in section 3 that it is, I think, a very smooth section to read. You can see how you can encode natural induction to refinement types via basically Curry-Howard correspondence. So in short, I presented complete verification using SMTs. The techniques are two. You use refinement reflection to basically reflect the implementation of functions into the refinement of the result type. And this means that every time you are applying a function, this translates to type-level computation. And then this allows you to prove many properties, but the proofs are big. So we use proof by logical evaluation that automatically unfolds your reflected function so that it shrinks the proofs. And all these are implemented and evaluated in Liquid Haskell. Thank you.
Hey, so you said that PLE is complete. What do you mean by completeness in this case? Because you would probably have to still call like inductive hypothesis manually and stuff.
You call all the limiter, you call all the inductive calls. Completeness, I mean that if there is an unfolding, a function that I can open to unfold to prove a thing, it is going to prove it based on the context.
When you're developing these proofs, what's the experience like when you don't have a complete proof? Like, how do you see the proof state and know what to prove next?
So personally, like I used reflection to prove stuff before PLE. So I did all the proofs manually, and it was like equational proofs that you have to do every step because otherwise it generates an error. And then, for example, like now what I do is I'm going to turn PLE on. I'm going to do the basic recursive call. And if it fails, I'm going to turn it off and do all the manual steps, and then maybe shrink it, maybe not shrink it. So generally, it is complete in the sense that you can prove everything. PLE helps a lot in the proof process, but we don't have any interactivity in the sense that if the proof, like if you have a proof in your paper, it is quite easy to make it. But there is no aid in helping you make the proof. This is hopefully a next step.
Thank you.
Could you say a bit more about how you actually tell the SMT solver about the unrolling, and especially when it depends on the context, right? So I guess the naive way of encoding it that you showed on a slide with just a for all quantifier gives the SMT solver access to the definition whenever it wants. But if it has to use some contextual information in order to be allowed to use that, do you encode that as a sort of fancy axiom, or
no. There is no axiom. There is no fancy coding. The only encoding is the thing that I saw it in the reflection side, that I say for the specific I, fib of I, the result is equal to fib of I, and also the syntactic definition, which means that by the basic dependent function typing rule, it means that when I apply the function, the reflected function, to my argument, then in the result, it is going to do the instantiation automatically.
But you mentioned that it's only allowed to do that if it knows some information about I.
Yes, because the information goes into the SMT solver. Because Liquid Haskell is case sensitive, so if you have this branching, all the information from the branches will go to the solver, so the SMT solver will decide what branch of fib of the reflected function to take.
Okay, thanks.
No problem.
Really cool stuff. I have a question about how you do case splits. Suppose I have a assumption in my context that says if B, an uninterpreted Boolean, is true, then I equals 1, else I equals 2. Now, if you see an occurrence of fib of I, do you do the case split in Liquid Haskell, or do you let the SMT solver do the case split?
The case split inside the definition of fib, or the case split in the proof?
No, there's an uninterpreted Boolean somewhere in their program that's telling you something about I.
So we don't do any automatic case splitting.
So
the user has to do all the case splitting.
I see. So in this case, the SMT solver would not know that the proof, maybe the proof could be done by the SMT solver by unrolling fib.
Yes, there is no unrolling, there is no case splitting. So if you remember the fib is increasing proof, I said that I can do all the unrolling as long as you give me the case splits. So we don't take any decision on case splitting. The user is responsible for this.
So the completeness of instantiation is, it does not take into account case splits?
No, just unfolding.
I see. All right.
And there's one question that got quite a few votes on Slido. The question is this: since you claim that your system is complete when it cannot prove a theorem, can it claim that the theorem is invalid? If yes, can you provide a counterexample?
No, because I claim completeness for PLE, and I claim completeness in the sense that you can do natural reduction. I don't claim that you are going to give P equals to NP into Liquid Haskell and it will tell you if it's valid or not. I am saying that if you give me a proof, I can check it with refinement reflection. If you can express the proof in the paper, you can encode it into Haskell term, and Liquid Haskell will check it. And also, this will be helped by the PLE automation.
All right, let's take an